All right, welcome back to Easy Math with Nick. Today we are on video number 8, and so I've taken I think exactly a 1 week break since my last upload, so I had other commitments to worry about, but here we are again. This is the next video in the sequence. Video 7 was a little deviation from the sequence I had posted in the description, my channel description, which is still relevant and up to date. So check that out if possible. Also check the poll that I've also posted on my channel for video number 12. You guys get to choose what topic that'll be on, so see that if you could. Without further ado, let's begin. Let me rename this. We're only doing one free response question today. I was planning on doing multiple. And one AP Stats FRQ. All right, give me a moment. I'll pause and paste it here because I don't think I pasted it here. Okay, so this is the question we'll be doing today. I think it's 2024 question 1. We'll come back to that later. Just wanted to post it there so we have it. Don't have to keep going back and forth. But today I just want to start off with, even though this question's mainly on, I think, hypothesis testing, if I recall correctly, I want to go over how you find a confidence interval. So, to put it quite simply, a confidence interval tells us with what certainty, for example, our mean lies within a range of values. So, if we have, let's say, the 95% confidence interval, we're 95% sure the mean lies within that interval. I'm not going to write that all out, but I'll just wait for that. Okay. So that's just a verbal definition of what confidence interval is, but how do you actually find it? And so before we find it, I just want to go over some, you could say, notation. We're going to be using what's known as, I think I call it the Z value. I think that's just what I'll be referring to it here. All right. So if we have Z sub alpha, this is where I was going with that. If we have a 95% confidence interval, our alpha is equal to 0.05. That's what I was getting at up there. Okay. So Z of alpha is the probability. Let me just write this out, what I have in my head first, and then I'll explain it. The probability that x is greater than z is equal to alpha. Greater or equal to z is equal to alpha. So when we look at our standard normal distribution, which is why we use the letter z, you could also, for different distributions, the notation uses different letters, as I'll show just in a moment. But if we have z sub alpha, this area here on our standard normal distribution, which is mean 0, variance 1. This area here equals alpha. Recall that standard normal distribution, as any normal distribution, is essentially a density histogram in function because the entire area has to sum up to 1. And so when we derive our confidence interval, we're going to have a scenario like this. Oh, that was horrible. Wow. It should be more flatted out at the tails. That's gonna have to do. I'm not that great at drawing these. My apologies. We're gonna have Z alpha. It's really gonna be Z alpha over 2, but I don't want to get too technical until we get to that point. Negative Z alpha. And because of symmetry, these two tails are both going to have an area alpha. I don't know what happened up here. Area alpha. Just draw an arrow here. But what about the center region? The center region is going to have area 1 minus alpha. Oh, 1 minus 2 alpha, sorry. In the example we'll do, it'll be 1 minus alpha, but here's 1 minus 2 alpha. So we're going to be taking advantage of that fact that for a normal distribution like this, the area under the curve is going to equal 1, as we expect it to be, because that's our total probability. That makes sense. I shouldn't have to explain that too much. So let's derive our confidence interval. So if we have, if we're going in, let's just start with the standard normal curve again. If we're, let's have our two values, alpha over 2. The reason we use alpha over 2 is because these two areas are going to give us alpha, as we just stated before. So the area on the inside is going to be 1 minus alpha. It's the area on the inside. And so between these two values, we're sure that what we're looking for here is the mean. We're sure that the we're going to be in between those two values with a probability 1 minus alpha. Whatever we're doing, we're going to do a confidence interval for the mean. So how we start out with is probability that the sample mean. We start off with the sample mean, and then we take a step further. 1 minus alpha. Probability that we're within this region is 1 minus alpha. But we don't really care about the sample mean. We want a confidence interval for the population mean. So we're going to we're going to standardize, which makes sense because we're using obviously the standard normal distribution. So that makes sense why we're doing that. See alpha over 2. Let me bring it down a little further. It's a little too close. Z sub alpha over 2. We'll see that alpha is typically 5% for examples, but it could also be 1%. It depends on the question. So standardize, because we're dealing with a sample, here our standard deviation, when we standardize, our standard deviation is going to be, because we're dealing with a sample, not the entire population. Population mean, I'm sorry, the population, square root of population variance divided by n. Make sure that's right. Yeah, that's right. And so, well, I guess there's the implicit assumption here that we know the population standard deviation, right? So there's a little bit of an implicit assumption there. But what if we don't? We'll get to that. We will most certainly get to that. So I'm going to put a little asterisk there because we will get to that very, not very shortly, but shortly enough. Still equals 1 minus alpha. And so now we want to have just mu in the middle. We want to solve for mu. So that population mean. So we're just going to, we're going to take this in 2 steps here. I don't want to go too quickly. I knew this video was going to be sort of on the longer side, but my videos are typically quite extensive. So I could do 2 steps at once, but I think I'm more than enough time to take it easy. All right. I just multiplied everything by the standard error on the bottom. Easiest way to say that without saying square root of variance over n. I guess that's also a little easier to say. But, all right, now we want to, I'm going to do 2 steps here. Actually, no, I won't. We're going to subtract the sample mean for all parts of the inequality here. Minus y bar, negative mu. I divide, my last step is going to be divided by a negative. And note, when we divide by that negative, that means we flip the signs. That's something to keep note of from algebra class. Still equals 1 minus alpha. And so, yeah, without further ado, we're going to flip the sides while as we divide each part of the inequality by negative 1. So we're going to have y bar minus z alpha over 2 standard error mu y plus z sub alpha over 2 1 minus alpha. And so finally, we have our confidence interval for mu. And so this tells us that there's multiple parts here to our confidence interval. This z alpha over 2, I was trying to think of a word for it. I'm pretty sure, 99% sure it's called the multiplier. So this is our, this is just dependent on what we choose for our alpha value. It's independent of whatever our population size is, our population variance, our sample mean. It's independent of that. That's what's called a multiplier. And this, as you heard me say multiple times, is also called our standard error. I don't know why I put this in quotations, but that is what it is. Yes, I still think it's called standard error, even though we're dealing with the actual population variance. It might be standard error if we're dealing with sample variance. I'm not quite sure. I'll leave that for now. I could come back, change that. Maybe I have to move this down, move that question down. Okay, but what if we, in what scenarios will we not use this standard normal distribution? Because there's other distributions as well. I mean, if you wanted to use, let's say, instead of the multiplier being z for the and using the standard normal distribution, in what scenario would you use students t distribution? So if we want to use that, that would be just a quick review here. Students t distribution with n minus 1 degrees of freedom with sub alpha over, I'm just going to, I think you use, I think it's a capital T. I think that's the correct notation. I'm sort of forgetting here. Please excuse me. So this is sort of the same idea we saw with the standard normal distribution, where the area z sub alpha is the that z value at which the area greater than that z value is equal to alpha. So that's sort of the same thing we see here, but instead of z, we're dealing with the students t distribution. And so I'm not going to rewrite this, but essentially this would just you would have, if you're using students t distribution, everything else stays the same, but only thing we're changing is that multiplier. So that would replace that if you're using the students t distribution, which I'll put that asterisk there now, because the asterisk from over here is what if we don't know the population variance. Then that's a scenario where we would use students t, because for students t, it's all right that it's okay that we use the sample variance as an estimate. So what if we, like two scenarios in which we would use students t over standard normal, which would be acceptable to do, is when we have, I won't go too in depth with this, but we can use note that for large sample sizes, it's not going to make a big difference which one you use. So if you have like a sample size of 1,000, which is I think what we see in this question down here, it doesn't matter. Oh, actually no, that was a population size. But I'm just for hypothetical sake, if we had an example where a sample size with 1,000 or a very obscenely large number, it doesn't matter which. It really doesn't matter which distribution you use, standard normal or students t, because you will get similar results, almost exact, as n approaches infinity. So if we use our standard, in the case that if n is like if we were using very small sample sizes, so if our n here, for example, show what I mean by n, is small, we most certainly want to use student's t-distribution. Unless we know the population standard deviation, which then we automatically default to using standard normal. So I think that I'm pretty certain that the threshold for that is if our sample size is less than 30. And also if we don't know the population variance. So if we use if we know the population variance, we would just default to using standard normal because that's the right choice. But if we don't, know it, then student's t starts to look like the better option. Unless, as I said, the sample size is extremely large. Over 30. Like well over 30, like 100 and more even. The difference starts to become very small. And so I think that's all I want to cover here. I'm not going to reiterate. I'm not going to write the entire confidence interval we had here, but just with the different multipliers for students t. I think you got the point with that. And so that's just how you find a confidence interval. So it's sort of closely tied to features of the standard normal curve and how there's that symmetry that goes on, as well as that the total area equals 1. That's a fact we definitely want to make use of and have in the back of our minds as we do this. Otherwise, it's not entirely clear what we're doing here. And also to note that we're starting off not with, we started off here with y bar and not the population mean. Because if we had the population mean, there's not much else to go with that. We start with the sample mean, and then we standardize to get to a point where we can then solve for population mean in the middle, as we did. No, that's sort of confusing how I just said that, but hope you get the point I'm getting at there. Anything else I wanted to harp on before we continue with that one question we have for today? And I think that'll be it. I think it's a quick one. There's not many parts to it. It's just one part. Sort of like the other, one of the other questions I did in my last statistics video. Yeah, I think this is capital T. Correct me if I'm wrong. I think that's the right notation. And I think even if we do know, I think the term standard error only applies if you don't, when you're using the sample standard deviation. It's the sample variance, and if you know the population variance, I think that's just what we have here is not really the standard error, and it's more just the sample, the expected value for the sample standard deviation, if that makes sense. Hopefully that made sense. I think I'm just going on a tangent here. Before I keep saying things that are probably wrong, I'll just move on. No, what we have here is definitely the expected value for the sample standard deviation. But if we use sample variance instead, and if we use sample variance and we don't know sample variance to estimate the population variance, I think that's when it becomes standard error. I'm pretty sure I'm right. I'll post a comment in the I'll post something in the description or a comment down below if I was wrong there. Hopefully I was. I think I'm okay. I think I'm okay with that. At first, before I was wrong, but I think I corrected myself there. All right, enough yapping. We finished our discussion on confidence intervals and how to derive them. It's time for our single AP Statistics free response question, FRQ. This is my second take of doing this. As my other take, I made a very silly mistake that I will actually explain to you so you don't make it, because making it mess some things up, to say the least. So without further ado, let me begin reading. A large exercise center. Oh, this is, by the way, this is question number 1 on the 2024 AP Statistics exam. I did not own this question. It's on my College Board. Fair use and everything, whatever. Let me read it. without further ado. A large exercise center has several thousand members aged 18 to 55 years and several thousand members aged 56 and older. The manager of the center is considering offering online fitness classes. Pretty cool. The manager is investigating whether members' opinion of taking online fitness classes differ by age. The manager selected a random sample of 170 exercise center members ages 18 to 55 years and a random sample of 230 exercise center members ages 56 and older. Each sample member was asked whether they would be interested in taking online fitness classes. The important part here is, does the opinion differ by age? So we're going to be comparing these two populations, sample population, very soon. Okay. Continuing, the manager found that 51 of the 170 sample members ages 18 to 55, 51 of the 170 for the 18 to 55 year group, and that 79 of the 230 sample members ages 56 and older said they would be interested in taking online fitness classes. At a significance level of alpha equals 0.05. This is important, by the way. Do the data provide convincing statistical evidence of a difference in the proportion for the younger group and proportion for the older group? Who would be interested in taking online fitness classes? So that just gives you the exact language that they talked about. Whether members' opinions, that's sort of more abstract. They're talking about proportions here. So as we're talking about proportions, let's define the proportion, what variable I'm going to be using for the proportions of both groups. So let me use black instead. So for a proportion for the younger group, I'll do P sub y, younger, y, younger. Population proportion for 18 to 55. And P sub O as in older. That's the rationale behind my choice here. Proportion 56 plus. Ages 56 and older. Okay. And they also gave us that alpha equals 0.05. So when we do our, when we find our p-value, we're going to be comparing that to our alpha to see whether we reject or fail to reject our null hypothesis. Okay. Speaking of null hypothesis, what is that? Our null hypothesis here is going to be that the proportions, the difference between the proportion, there's no difference. So P sub y equals P sub 0, or that could be rewritten, more useful to rewrite it as the difference is equal to 0. And our alternative hypothesis, as they give us, is that there is a difference. So the difference is they're not equal. Which could be rewritten as the difference is not equal to 0. That should make sense. And so we can find our test statistic. Let's find our sample proportions for both groups. So for the younger age group, our P sub y hat, as we'll call it, is going to be, they gave 51 over 170, which is equal to 0.3. I have that on my calculator. I'm going to double check that just before. Yep, that's right. And for the older group, it's going to be 79 over 230, which is 0.343. So not that much of a difference here. That might be pointing to supporting the null hypothesis. But we can't just say that yet. We can't just stop there. We have to actually find the value of our test statistic. So because we're doing a two-sample test here, for technical reasons, we don't, even though we're assuming our null hypothesis is true, we don't exactly know our population standard deviation. So we can't technically we would use what's known as a test statistic T, where we use the standard error instead. But because our sample sizes are quite large, we don't have to worry about that notation between using this test statistic Z or test statistic T in those two different scenarios, whether we know the population standard deviation or not. So that just gets very confusing. So I'm just going to use Z, as I think we use that in I talked about that when we were talking about confidence intervals. We use the standard normal distribution. So I'm going to use the standard normal distribution here. So I'm going to use Z. There shouldn't be much of a difference anyway. So just to explain my rationale there. There's probably like absolutely none of you that care that much, but just for notation's sake, because it might raise a mental flag for some of you. So if we want to find our test statistic Z, be the difference between the two sample proportions minus 0, because the 0 is what we hypothesize. We're assuming no hypothesis is true whenever we're doing hypothesis testing. So if we assume no hypothesis is true, the difference between the two proportions is going to be 0. The two population proportions is going to be 0. So when we find that test statistic, we're subtracting 0 there. And on the bottom, we're going to have the standard error of that difference. Which, at first, I thought, when I did this during my first take, let me just plug this into the standard error equation for one population, or one sample, sorry. But no, that's not right. To make sense of how we find this, let's start out by how we would find the variance of this difference here. So the variance of this difference, we sort of break this up and then do a slight linear transformation. In big boy words, what that's going to mean on paper. Variation 1 plus, not minus, variation of the other one. I'll stick to the curly brackets. The reason we're doing addition here is because, say we had y equals ax plus b. The plus b doesn't affect variance, so I'll just get rid of it. Variance of y is going to be a squared times variation of x. And this makes sense when we think about just that standard equation for variance. We're squaring values. And so we don't have a square root like we do in standard deviation. So we're not just multiplying by a, we're multiplying by a squared. And so that's why this negative here, when we break it up, which is something you could do if you didn't know that, that negative that's going to be within here comes out as a positive because we can square that negative. There's technically a little nested -1 there that comes out and we square it, so it becomes a 1. So that's why there's no negative sign in there. Just to be technical, to show how we're doing this and why it makes sense. And so if we wanted the standard error, it's going to be the square root of this. So take square root. Should draw arrows to see where we're going here. And so it's going to be py hat 1 minus py hat. Now we can use that. I use ny hat because I'm sorry. Why I use I'll explain it when I get to it. My second take. So sort of getting a little tired by now, but it's okay. I use n sub y and n sub 0. I said ny hat, whatever. N sub y, n sub 0 to indicate that this is the sample for the younger group. This is the sample for the older group, to make it less confusing. So that's just what those variables I indicated mean. And so if we're trying to find the test statistic Z, I'm sorry, if we're trying to find the standard error, we're not quite at the test statistic yet. This is just what's going to be in the denominator. Our sample proportion for the younger group is 0.3, 1 minus 0.3, 0.7, over the sample size for that younger group, which is 170. 0.343. sample proportion for the older group. And over here, it's going to be 1 minus 0.343. 0.657 over 230. If you crunch the numbers here, I think I got this down. All right, this is going to give you that standard error. It's equal to 0.0471. Look at that. Now that we have this, we have what's going to be in the denominator up there. So now we want to find what the difference between two sample proportions we have is. So P y hat minus P0, P sub O, not 0, hat is going to be 0.3 minus 0.343, which I could do that in my head. It's going to be negative 0.043. So there you go. Now let's find our test statistic finally, after all this hard work. I did my mental math there, right? I don't know why I had to check, but it took me a while to get to this point, so you don't want to do anything wrong, right? And our test statistic Z is going to have the value of negative 0.913. There you go. All right, so when we go to interpret this to find our p-value, we want to draw our standard normal curve. And so if we draw badly drawn standard normal curve here, because our alternative hypothesis was that the two proportions are not equal, the two population proportions are not equal, we're going to have two tails to our standard normal curve when we go to find our p-value. I won't delve into why that's the case, but I might have done that in a prior video, but maybe in a future video I'll explain that. But for time's sake, our p-value is going to be the combined area of these two little regions here. And this is our standard normal distribution that I said I would use before. Instead of student's t, which would be complicated because how many degrees of freedom you use, I think there's a complicated, you have to do some complicated calculation for that, so I'm not going to do that today. So now if we look at our standard normal charts, I have them pulled up here. Oops. Where are they? Right here, standard normal chart. If we go to negative 1.9, negative 1.9, what's our decimal 0.9, 0.91, negative 0.91, so negative 0.91, going to be 18.14, all right, 0.1814, 0.1814, so the area for one of these tails is 0.1814. Because of symmetry, as we stated before, area for these, both of these individually, 0.814. So p-value is going to be 2 times that. 0.814. And so it's going to be 0.3628. That I could do mentally. I'll do it in the calculator too because we're already using so much time, right? Yep, that's right. And so just by looking at that, that's pretty large p-value. That is well above, if we compare that to our alpha, which is 0.05, p-value is much greater than alpha. So 0.3628 is much greater than 0.05. It's like 7 times greater. So that indicates that we cannot reject null hypothesis in favor of alternative, so we failed to reject it. And in context, what that means is there's not convincing statistical evidence that there is a difference between the proportion of members in both age groups that would be interested in taking the online fitness classes. So I'm not going to write that out, but to restate that, the difference between the proportion of members in both age groups that would be interested in taking the online fitness classes, there's not enough statistical evidence to state that there is a difference, because our p-value here was so large that given our sample proportions of the two groups, we can't say that those sample proportions are different enough to warrant to support the alternative that the difference between the actual population proportions is not zero, if that made any sense. So there you go. But linking back to our conversation about confidence intervals, so let's say we were not, let's say this question was phrased differently. Let's say we weren't given the sample proportions at all of the two groups, and we were just given a confidence interval for the difference. So let's say we were given a 95% confidence interval for the difference between and this was 0.1, 0.2. So we know with 95% certainty that the difference is between that region. So let's say we did this. What our alternative hypothesis, our null hypothesis is still that the difference is equal to 0. And alternative is also the same. We're not changing the question here, just changing what they give you. So now, do we have enough? How does our answer change? Well, it would change because now we have enough evidence to support to in favor of the alternative against the null hypothesis. Because if we look here, this at the 5% level, we're still at the 5% level. So at the 5% level here. So at that 5% level, we're 95% sure that we're within this interval. But if we were, let's talk about a larger interval. Let's say we had negative 0.1 to 0.2. Well, then we wouldn't be 95% sure anymore. We would be more than 95% sure. So the probability of it being within that range is going to be greater than 95%. Let's say it's 98%. And so our alpha, so to speak, would be lower, would be smaller. So that sort of correlates to, mentally this is hard to express, but essentially if we were using that interval instead, our p-value would be smaller than 5%. So we could say that we could reject the null we could reject the alternative in favor of the null hypothesis. Fail to reject the null hypothesis, what I should say, in that scenario, because we're 98%. Let me think of how I want to express this. Yes. So yeah, at the 5% level in this case now, we can say that okay. I'm just trying to see if I'm saying anything wrong. No, I think what I'm saying is right. At the 5% level here, we can't reject the null hypothesis in favor of the alternative. Yes, we fail to reject. Okay. Let me think here. All right, I think that's all I wanted to cover today. So that was just a little hypothetical. What if they gave you a confidence interval? But I think that's about it. This video is getting a little bit too long. I I went on for long enough without saying anything completely incorrect, I think. So that's about it. So that's all I wanted to cover today. Thank you for listening to my rant for video number 8, deriving confidence interval and an AP Statistics F1 AP Statistics FRQ on top. Thank you.